From Michael Faraday's experiments, we know that if we have a closed surface, the amount of electric flux coming out through that closed surface is equal to the charge enclosed. Gauss's law is a mathematical description of that. The integral of the dot product between the electric flux density field and the surface differential over that surface is equal to the charge enclosed. So this little circle on the integral indicates that we are integrating over a closed surface. Let's look at the role this dot product plays in determining the amount of flux coming through our surface. Let's assume we have a uniform electric flux density field that is normal to the plane of this page, so these dots represent the orientation of this vector field coming up out of the page. And let's give it a value. Let's say the magnitude of the electric flux density field is 2 microcoulombs per square meter. Now let's assume this surface has a cross-sectional area of 1 square meter, and this dot represents the orientation of this surface, so it represents the direction of the unit normal to this surface. When this unit normal is in the same direction, in other words, the angle between this unit normal and our electric flux density field is 0, then this surface lies in the plane of our page, and the amount of flux, the amount of these dots going through this surface, gives us the amount of electric flux going through the surface, which is just the electric flux density field of 2 microcoulombs per square meter times the surface area of 1 square meter, or 2 microcoulombs of electric flux coming through this 1 square meter. Now, if we change the orientation such that the unit normal is at 90 degrees to the electric flux density field, we see that none of these dots coming up out of the page are going to go through our surface, so the amount of flux going through it is 0. Now, if the orientation of this unit normal and the vector field is somewhere between 0 and 90 degrees, now some flux will go through it. And the way to determine that is to take the projection of this surface onto the plane of the page. So this will give us some cross-sectional area in the plane of the page that is going to be less than the 1 square meter of our surface here. Now let's take a look from the edge from the right side here. I'm going to now call the surface area delta S, and it's going to be oriented like this with some angle theta with respect to the electric flux density field. So the projection of the area on a plane that is normal to our electric flux density field is shown by this segment right here. Now, if the angle is theta between our surface element and the electric flux density field, the angle here between our surface element and the projection of our surface element is also theta. So the cross-sectional area here will be the hypotenuse delta S times this angle cosine of theta. So the amount of electric flux going through this plane will just be this area, delta S cosine of theta, times our electric flux density field D. And this is just the definition of the dot product between two vectors, the electric flux density field and our surface element delta S. If we take the limit as delta S goes to 0, then we can write this as d psi is equal to d dot ds. Okay, so then if we integrate d psi over a closed surface, we get the flux coming out of our surface, our closed surface, and that's going to equal the charge enclosed. So there we have Gauss's law.